if vector u is linearly dependent of vectors v1 to vn, if u is a linear combination of v1 to vn. So this is actually just giving new name to old stuff. However, a more interesting definition is when the opposite of this happens. I'm gonna say that vectors v1 to vn are linearly independent when the opposite of the above happens. So that means these vectors v1, v2, and so on to vn, they are not dependent. So not one of these vectors can be written as a linear combination of the others. In a way, these vectors, they are kind of unrelated. I cannot write anyone as a linear combination of the other vectors. The mathematical way of saying that is to say that the only solution to these vectors equation x1, v1, so this x, this is my variable, and this v, this is my vector. So these x here, they are the unknown variable. So if x1 times v1 plus x2 times v2 plus and so on until xn times vn, and I set that equal to 0, again my x are the variable, my x are the unknown. If when I solve this vector equation and the only solution that I have is all the x equal to 0, then I'm gonna say that these vectors are linearly independent. Notice that the 0 when all the x are equal to 0 is automatically one of the solutions, because if all the x are 0, then my left hand side is automatically 0. So if this is the only solution, then I'm gonna say that these vectors are linearly independent. Now to demonstrate, let me actually just do the example 5.1 here. I'd like to solve the following systems. Notice how, well, actually I recycled these numbers from example 4.1, 4.2, and 4.3, so I'm just gonna say 4.3. So I actually recycled these numbers from the example in the last lecture. In the last lecture, we see that 11, 4, 15 is actually a linear combination of the two vectors here, 1, 2, 9, and 5, 1, 3. And in the other one, these vectors of negative 3 and 5, 6 is not a linear combination of these two vectors. So let's kind of see what will happen when I try to solve this vector equation x times this guy plus y times this guy plus c times this guy equal to 0. So let me just do what we usually do. So I'm gonna rewrite this as the augmented matrix. So I'm gonna collect the variable, the constant. That's gonna be 1, 2, 9, and then 5, 1, 3, and then 11, 4, 15. My right hand side, that's gonna be 0, 0, 0. Now then, I will reduce this guy, and what I'm gonna get is, well, let me just write the final form. The reduced row echelon form for this guy is gonna be 1, 0, 1, 0. And then 0, 1, 2, and then 0, 0, 0, and then 0, 0. And what does this mean? This means the solution for the system, I'm going to have my c as a free variable. So the solution for the system is going to be a c. My x is going to be negative c, and my y is going to be negative 2c. Okay, so this is the solution for this system. Notice that my c can be anything. So the solution for this guy is anything where x equal to negative c, my y equal to negative 2c, and then my c can be anything. So the solution for this system is a lot more than just the 0 vector. So what I can tell from this is that these three vectors, 1, 2, 9, 5, 1, 3, and then 11, 4, 15, they are related. So these three guys are not linearly independent. Okay, so let's see what's going to happen in the next case then. I have this thing. So let me once again put this into the augmented matrix. I'm gonna have 1, 2, 9, 5, 1, 3, negative 3, 5, 6, and 0, 0, 0. Okay. So I can go ahead and row reduce this guy. I'm gonna get 1, 0, 0, 0, 1, 0, 0, 0, 1, and 0, 0, 0. Voila. Now, what does this mean? This means the solution for this system is actually just x equal to 0, y equal to 0, z equal to 0. So, the only solution to this is 0, 0, 0. So that means these three guys, they are linearly independent. So these three guys, 1, 2, 9, and then 5, 1, 3, and then negative 3, 5, 6. These three guys are indeed linearly independent. So not one thing is a linear combination of the other two.